Assalamualaikum warahmatullahi wabarakatuh. We are from Group 3. My name is Rukaya Al-Qudsia binti Cik Azlan. I will elaborate for the abstract of this project, which is the impact of pavement compaction levels and their alignment with the Malaysian Public Works Department standards. Our primary objective was to investigate how different compaction levels affect key performance metrics such as dry density, tensile and compressive strengths, rut depth and resilient modulus. We use theoretical stress distribution models to understand the effects of compaction on pavement layers and their ability to manage stress under real-world traffic conditions. We conducted rigorous testing and analysis on pavement samples subjected to various compaction levels. These samples were assessed for their ability to withstand stress and deformation under cyclic loading conditions, which simulate traffic loads. Our key findings show that higher compaction levels significantly improve dry density and structural capacity, effectively managing tensile and compressive strengths and reducing pavement distress. Lower rut depth and higher resilient modulus values indicate better pavement performance. In summary, proper compaction practices are crucial for ensuring long-term pavement durability, reducing maintenance need, and providing a reliable transportation infrastructure.
Assalamualaikum warahmatullahi wabarakatuh. My name is Nur Shada and I'm going to present about the introduction part. So the purpose of this study is to conduct a comprehensive evaluation of the structural condition of asphalt pavement using an advanced pavement software analysis supported by laboratory testing result. So the study is aimed to identify and analyze common asphalt pavement distress which are indicative of underlying factors such as lack of structural capacity, inadequate design, and inferior material quality. This project aims to leverage MATLAB for the detailed evaluation and analysis of asphalt pavement distress based on the laboratory testing results. So by systematically assessing and categorizing distress types, quantifying their severity, and identifying contributing factors, so the project seeks to provide comprehensive understanding of the current structural condition of pavements under study, recommend target maintenance and rehabilitation strategies to optimize infrastructure investment and improve long-term pavement performance, and lastly, contribute valuable insight and empirical data to inform policy decisions, enhance infrastructure resilience, and support sustainable transportation development. In another word, proper compaction in road construction is crucial for several key reasons, which is for example, strength and stability. Inadequate compaction ensures that the layer of material in the road structure are densely packed. Next is uniformity and smoothness. Effective compaction helps in achieving uniform density throughout the pavement layers. Next is durability and longevity. While compacted roads are most resistant to moisture infiltration and subsequent damage from freeze-thaw cycles. Next is optimized material usage. Efficient compaction practice minimize voids within the pavement layers, optimizing the use of materials such as aggregate asphalt and stabilizing agent. Next is environmental benefits. The proper compaction supports sustainable road construction practice by reducing the need for additional materials and lowering this construction-related emissions. Next, operational efficiency. Roads are well compacted, experience fewer maintenance issues and disruption. Then, compliance with standards and specification. Proper compaction ensures that the road construction meets design specification and standards set by regulatory authorities. So in the conclusion, proper compaction in road construction is essential for build durable, safe and cost-effective transportation infrastructure. It underpins the structural integrity, longevity and environmental sustainability of roads, benefiting communities, economies and the environment alike. Next is the standard of specifications referred in the project. In conducting a study to evaluate the structural pavement condition and identify common asphalt pavement distress using MATLAB, it is essential to adhere to relevant standards and specifications. These standards provide guidelines for pavement design, material testing, and performance evaluation, ensuring consistency and quality in infrastructure management. So this is the standard and specification, which is ASTM International Standards. It's going to ASTM D5340, which is Standard Test Method for Airport Pavement Condition Index Surveys. This standard outlines procedure for conducting pavement condition surveys to assess condition of airport pavement, including the stress identification and severity rating. Next is ASTM D6433, which is Standard Practice for Roads and Parking Lots Pavement Condition Index Surveys. Next is ASH2 Standards which is H2R330. It is standard practice for mixture conditioning of hard mix of asphalt (HMA). Then H2T283 standard method of test for resistance of compacted hot mix asphalt to moisture-induced damage. Next is Federal Highway Administration (FHWA) guidelines. FHWA HIF 07021 Pavement Distress Identification Manual. FHWA RD03031 user guidelines for waste and byproduct materials in pavement construction. Next is Local and State Department of Transportation (DOT) specification, which is local and state DOTs often have specific pavement and design and evaluation standard that align with regional climate condition, traffic characteristic, and environmental consideration. These specifications include material specification, design standard, performance specification. So adhere to this standard and specification ensures that the study of pavement distress evaluation using MATLAB is conducted systematically and reliably. By referring established guidelines, the project aims to maintain methodological rigor, enhance credibility of finding, and facilitate comparison with industry benchmarks. So this approach supports informed decision-making and pavement management, promotes sustainable infrastructure practice, and contributes to advancement of transportation engineering knowledge. So that's it.
Hi and Assalamualaikum. My name is Fatimah Sarah binti Azman and I will presenting methodology. Okay, the methodology section of our project is outline the systematic procedure and technique used to conduct the study and achieve the research objective. It serves as a blueprint for how the research was carried out, ensuring that the study can be replicated and validated by others. So this is my flowchart. This is our flowchart for our methodology. Okay, first we start with start, and then we have to do material preparation, which is we have to obtain crushed granite and sieve according to JKR. And then we do compaction test. Next, repeated triaxial load test, and then we have to conduct resilient modulus test. After all this, we have to do a design analysis using MATLAB. Our group has choose to use MATLAB as it was easy to conduct. And then this was the end of our methodology. Okay, that's all for me. Thank you.
So I will continue with the design using MATLAB software. First, dry density at different degree of compaction. This bar chart illustrates the dry density of the aggregate specimens at 90, 95 and 100% compaction level. The dry density increases with the degree compaction, indicating that higher compaction level result in a denser aggregate structure. Next, main principal stress at different level. This graph shows the main principal stress experienced by different layers of the pavement, specifically the lower subbase, upper subbase and base across various stress levels. Next, as the stress level increases, the main principal stress in each layer also increases. The lower subbase, the foundation layer, start with lower stress and increase steadily as the load condition escalate. Next, the upper subbase experience higher stress than the lower subbase under the same load condition. The base layer situated directly under the asphalt bear the highest stress in it is closest to the surface load such as traffic. It must be the strongest layer to prevent pavement failure like cracking and rutting. Next, cyclic axial stress at different levels. The line graph presents the cyclic axial stress for different pavement layers. It helps in understanding the cyclic loading effect and potential deformation patterns. The line graph shows how the amount of stress changes over time in various layers of pavement subjected to repetitive load. Each line on the graph represents a different layer within the pavement structure. The top layer experiences the most stress directly from traffic, while deeper layer encounter less stress. The graph shows how this stress varies over repeated cycle of vehicle. Resilient modulus at different stress level and compaction degrees. The graph shows how the resilient modulus, a measure of material stiffness, change under different stress level and degrees of compaction. Each line shows how the resilient modulus varies as the stress applied to the pavement increase. For instance, at higher stress level, the resilient modulus tends to decrease, indicating the material become less stiff and more prone to deformation. Higher compaction level generally result in higher resilient modulus value, suggesting greater stiffness and better resistance to deformation. Next, we have tensile strain in asphalt layer, comprehensive strain at the top subgrade, and rut depth in asphalt layer. Firstly, tensile strain, which measure how materials stretch under load, show consistent behavior across various stress levels for each compaction level. The consistency highlights the predictable relationship between applied load and the material stiffness. Secondly, comprehensive strain in the top subgrade layer varies with both stress level and compaction percentage. The variation affects the structural integrity of the pavement, indicating how well the pavement can withstand downward pressure from the traffic. Lastly, rut depth in asphalt layer increased notably with higher stress level and lower compaction percentage.
As for discussion, dry density increases with higher compaction levels. Higher compaction results in a denser aggregate structure according to standard like AASHTO. Optimal compaction is crucial for structural capacity. Higher dry density enhances load-bearing capacity and prevents structural failures such as cracking and rutting. Target compaction levels are specified, such as at least 95% of maximum dry density from proto tests. Adequate compaction reduces void spaces, leading to a stronger pavement whereas the structure distributes stress more evenly, reducing deformation and maintaining smoothness. Finding from Figure 1 with existing standards showing higher compaction increase dry density. Proper compaction is essential for strong, durable, and long-lasting pavements, reducing maintenance and ensuring reliable infrastructure. From Figure 2, principal stress increase with high stress levels across pavement. Low subbase experiences the least stress, while the upper subbase and base layer experience progressively higher stress. Crucial for effective load management within the pavement structure. Proper compaction ensures uniform stress distribution across layers, prevents localized failures, and maintains structural integrity. Higher compaction minimizes deformation under load, reduces potential stress concentration points that could lead to cracks and pavement distress. Finding from Figure 2 align with Malaysian pavement design standards. Optimal compaction improves stress distribution, load-bearing capacity, and reduces failure, ensuring strong, durable, and long-lasting pavement capable of withstanding traffic and environmental conditions. Discussion for Figure 3 varies over time to different pavement layers. Top layers experiences the most stress, which decreases with depth, enhances the ability of layers to withstand cyclic loading, reduces deformation, and prolongs pavement life. Must withstand the highest level of cyclic loading due to direct traffic contact. High compaction helps distribute traffic-induced stresses, reducing deformation and wear. From JKR guidelines emphasize achieving optimal compaction for durability and performance under repeated traffic loads, and surface cars should be compacted to specified density using appropriate equipment and techniques. Finding from Figure 3 show higher compaction enhances the ability to withstand cyclic axial stress. Adhering to these standards help design pavement that effectively manage cyclic loading, minimize deformation, and prolong pavement life. Achieving optimal compaction across all layers is crucial for durable, high-performance roadways in Malaysia. Discussion for Figure 4, resilient modulus measures material stiffness. Higher convection levels, which are 90%, 95%, and 100%, result in higher resilient modulus values. Indicates greater stiffness and better resistance to deformation. At the higher stress levels, resilient modulus decreases, showing the materials become less stiff and more prone to deformation. Critical for maintaining high material stiffness and resisting deformation under load. Higher resilient modulus indicates a stiffer material that can better resist deformation under traffic loads. Resilient modulus decreases, indicating materials become less stiff and more prone to deformation. from Malaysian pavement design standard, incorporate horizontal modules values to ensure pavement structures can withstand applied load without excessive deformation. Values are used to assess the suitability of material for different pavement layers. Finding from Figure 4 outline with standard emphasizing optimal compaction to enhance horizontal modulus and maintain high material stiffness. Adhering to these standards ensure pavements resist deformation under load, ensuring durable and high-performance roadways. Guidelines provide detailed specification for compaction levels and resilient modulus values for long-term durability and cost-effectiveness. Discussion for Figure 4 tensile strength are consistent across stress levels for each compaction level, indicating a predictable load-material stiffness relationship. JKR guidelines specify limits to ensure long-term performance, varies with stress levels and compaction percentage, influencing structural integrity control to prevent excessive deformation according to Malaysian standards. Higher compaction reduces compressive strain, maintaining subgrade integrity, increases with higher stress levels, and lower compaction indicating deformation risk. Higher compaction enhances stiffness, reducing rod depth, and improving load resistance. From Figure 5 analysis shows that tensile strain in alpha, compressive strain at the top, a subgrade, and rod depth in alpha. Finding aligns with Malaysian standards, highlighting the importance of proper compaction in controlling strains and minimizing rod depth for durable pavement. Design standards and JKR guidelines emphasizes higher compaction levels to increase dry density meeting structural capacity standards. For the hierarchical stress distribution, Figure 2 shows the stress distribution across pavement layers, lower subbase, upper subbase, base aligns with Malaysian standards, ensures different layers manage varying stress levels for structural integrity. For the mitigating cyclic loading effects, Figure 3 highlights the role of compaction in mitigating cyclic loading effects, aligned with Malaysian standards emphasizing high compaction for pavement resilience under repeated traffic loadings. For the resilient modulus, Figure 4 findings on resilient modulus reflects adherence to Malaysian criteria for stiffness, essential for withstanding traffic-induced stresses and maintaining pavement integrity. Lastly, for the control of strains and rod depth, Figure 5 shows controls of tensile and compressive strains and rod depth, supports adherence to Malaysian guidelines for minimizing pavement distress and ensuring long-term durability through effective compaction practices. For the overall consistency with standards finding demonstrate the consistent alignment with Malaysian pavement design standards, ensure durable high-performance roadways that meet stringent performance criteria and reduce maintenance need.
In conclusion, our study highlights the importance of achieving higher compaction levels to enhance pavement performance and meet JKR standards. Proper compaction reduces tensile and compressive strains, minimize rod depth, and improve resilience, resulting in longer lasting and smoother pavements. The study emphasized the need for rigorous quality control, advanced equipment, and thorough testing during the compaction process. By adhering to these standards, we can construct durable roadways that require less maintenance and support sustainable transportation networks. Ultimately, following JKR compaction standards is vital for creating safer and more efficient road infrastructure. That's all from us. Thank you.